The universe holds secrets we are only beginning to touch. Far beyond our own Milky Way spins one of its most stunning and chaotic creations, the Pinwheel Galaxy. Known to astronomers as M101, this magnificent spiral is not just a pretty picture, it is a cosmic treasure chest overflowing with bizarre and unexplained events. In this journey, we will unlock 25 of its strangest phenomena. You will discover everything from stellar explosions that defy physics to celestial structures, so odd they hint at entirely new cosmic laws. By the end, you will see a familiar corner of the cosmos transformed into a theater of profound mystery. How can a galaxy's core hide a missing monster, and what could cause a star to behave in ways theory says are impossible? What single cosmic question does the Pinwheel Galaxy make you most curious to solve? Our first mystery begins with a flash of light so brilliant it outshone an entire galaxy. In 2011, astronomers watched a star die in the Pinwheel Galaxy. They catalogued it as supernova PTF11 Cly, a standard type IR event, but nothing about it was standard. It was impossibly bright, radiating more energy than the laws of physics said it should. This was no ordinary stellar death. It was a Super-Chandra supernova, a name that points directly to the heart of the puzzle. The Chandrasekhar limit is a fundamental rule in astrophysics, named for the Nobel laureate Subramanian Chandrasekhar. It states that a white dwarf, the dense corpse of a sun-like star, cannot weigh more than about 1.4 times the mass of our own sun. If it gains more mass, perhaps by siphoning material from a companion star, it becomes unstable and triggers a thermonuclear explosion so precise it always reaches the same peak brightness. This consistency makes Type IR supernova cosmic measuring tapes used to gauge vast distances across the universe, but PTF11 Cly was too bright. Its luminosity suggested the exploding white dwarf was far heavier than the Chandrasekhar limit allowed. How could that be? The discovery shattered a comfortable assumption and forced scientists to consider wilder possibilities. Perhaps two white dwarfs spiraled together and merged, creating a single, overweight monster that then detonated. Or maybe the white dwarf was not made of the usual carbon and oxygen, but of heavier elements like neon and magnesium, which could alter the physics of its demise. The Super-Chandra event became a focal point for debate, a single flash of light proving that our textbook models of stellar death are incomplete. If the standard candle used to map the cosmos is not so standard after all, what does that mean for our understanding of the universe's expansion or even its ultimate fate? The Pinwheel Galaxy offered not just an anomaly but a direct challenge to a cornerstone of modern astrophysics. That supernova was a warning that the Pinwheel Galaxy plays by its own rules. Its next strange phenomenon offers a more persistent and perhaps more profound puzzle. Deep within one of its spiral arms, astronomers have pinpointed a single point of light that blazes with the fury of millions of suns, but not in the light we can see. This object, catalogued as M101 ULX-1, is an ultraluminous X-ray source. In simple terms, it is a cosmic beacon screaming in the high-energy language of X-rays. Its brilliance is staggering, shining hundreds of times brighter than any typical X-ray binary, a system where a black hole or neutron star feeds on a companion star. The sheer power output defies a fundamental law of cosmic dining known as the Eddington limit. Think of a black hole like a cosmic vacuum cleaner pulling in gas from a nearby star. As that gas spirals in, it heats up to incredible temperatures and glows brilliantly, but there is a catch. The light itself exerts an outward pressure. If the black hole eats too fast, that radiation pressure becomes so strong it can actually blow the incoming gas away, like a leaf blower fighting a vacuum cleaner. This balance point, where the inward pull of gravity equals the outward push of radiation, is the Eddington limit, It sets a theoretical maximum for how brightly any object of a given mass can shine. M101 ULX-1 laughs at this limit. Its luminosity is so extreme that if it were a typical stellar mass black hole, weighing perhaps 10 times our Sun, it would have to be consuming material at a rate far beyond what physics says is possible. It is a cosmic glutton on an impossible diet. This forces astronomers to consider two equally thrilling possibilities. The first is that this is not a small black hole at all, but an intermediate mass black hole, a long-sought missing link between the small stellar remnants and the supermassive giants at galaxy centers. An object weighing thousands of solar masses would have a much higher Eddington limit, allowing it to shine this brightly without breaking the rules. The second, more revolutionary idea is that our understanding of the rules is wrong. Perhaps under certain extreme conditions, matter can be funneled onto a stellar black hole in a new way, like a dense, focused fire hose stream that bypasses the radiation pressure, allowing it to shine in a super Eddington state. This ultraluminous source is more than a bright spot. It is a laboratory testing the very limits of how gravity and light interact around the most extreme objects in the universe. Yet the Pinwheel Galaxy's defiance of cosmic rules is not limited to brilliant explosions or gluttonous X-ray beacons. It extends to its very heart, where we find a profound and unsettling silence. At the center of most grand design spiral galaxies, including our own Milky Way and our neighbor Andromeda, lurks a supermassive black hole. These are monsters of staggering scale, millions to billions of times the mass of our Sun, and their gravitational grip dictates the motion of stars around them, often announcing their presence with brilliant, swirling disks of hot gas or powerful jets of energy. But when astronomers point their most powerful telescopes at the core of the Pinwheel Galaxy, they find nothing, or at least nothing like what they expect. There is no clear, concentrated radio source, no brilliant X-ray flare from an active feeding frenzy, no telltale dance of stars orbiting an invisible, monstrous mass. The core of M101 is quiet. This absence is deeply unusual. A galaxy of its majestic size and perfect spiral structure should, by all our models, host a central supermassive black hole. Its absence is a gaping hole in our understanding, a missing keystone in the galactic architecture. So where did it go? Scientists have proposed several compelling and strange theories to explain the silence. The first possibility is that the black hole is simply dormant, a sleeping giant. It may have consumed all the nearby gas and dust in its vicinity, leaving it with nothing to feed on. Without a meal to heat up and glow, it becomes dark and nearly impossible to detect directly, like a predator lying in wait in a pitch-black forest. Another idea is that the black hole is there, but it is unusually small for such a large galaxy. Perhaps the Pinwheel Galaxy formed or evolved in a way that prevented its central black hole from growing to the colossal sizes we see elsewhere. It could be a lightweight champion in a heavyweight galaxy, its gravitational influence too faint to easily spot amidst the bright core stars. A third, more practical explanation is obstruction. Thick clouds of cosmic dust and gas could be shrouding the galactic center, blocking our view of any high-energy emissions from an active black hole. We might be looking at a brilliantly lit stage through a heavy, dark curtain. The contrast with our own galactic neighborhood is stark. We know our Milky Way's central black hole, Sagittarius A star, has a mass over 4 million times that of our Sun, and we can see stars whipping around it at incredible speeds. Andromeda's is even larger. Their activity, even when quiet, is confirmed. The Pinwheel Galaxy's silent heart forces us to question a fundamental assumption. Is a supermassive black hole a required component for a beautiful spiral, or can a galaxy achieve such grandeur through other means? This quiet center may be hiding the most revolutionary secret of all. This architectural oddity is not a flaw but a clue to a violent past. While the Pinwheel Galaxy presents a near-perfect face to us, a closer look reveals a striking imbalance. Its spiral arms, those graceful arcs of stars and gas, are not symmetrical. One arm, typically the southern one, appears noticeably brighter, more ragged, and more extended than its counterparts. It is as if the galaxy is favoring one side, bearing a luminous scar from an old wound. This is no trick of perspective or an optical illusion. It is a real and profound distortion in the galaxy's very skeleton. The leading explanation for this asymmetry is a cosmic collision, a close gravitational encounter with a smaller dwarf galaxy sometime in the distant past. Picture a stone thrown into a still pond. The ripples spread out in concentric circles, disturbing the water's surface. Now imagine that stone, a small galaxy, passing very close to the edge of the pinwheel. It would not smash directly into the disk, but its immense gravitational pull would act like a tidal force, stretching and pulling on the stars and gas in that region. This gravitational tug-of-war would compress vast clouds of hydrogen gas, the raw material for new stars. When you squeeze a cosmic gas cloud, you trigger a chain reaction. The increased density causes pockets within the cloud to collapse under their own gravity, igniting the fires of nuclear fusion and birthing new stars. This is what astronomers call a starburst, a ferocious wave of star formation. The brighter, distorted arm is essentially a stellar nursery operating at a frenzied pace, illuminated by the brilliant light of millions of newborn suns, many of them massive, hot, and blue, which shine with extraordinary intensity. The encounter left a dual legacy. First, it sculpted the arm's shape, pulling it out of its perfect spiral symmetry. Second, it lit a fire within it, a burst of stellar birth that continues to glow brighter than the rest of the galaxy's more sedate star-forming regions. This phenomenon transforms our view of the pinwheel from a static portrait into a dynamic history book. That asymmetrical arm is a chapter written in light, detailing a moment of chaos and creation that reshaped the galaxy's destiny. It reminds us that even the most serene cosmic structures are born from and bear the marks of ancient violence. That ancient violence did more than just reshape an arm. It may have launched individual stars on journeys of impossible speed. Scattered across the Pinwheel Galaxy are celestial fugitives, stars moving so fast they are essentially escaping the galaxy's gravitational grasp. These are hypervelocity runaway stars, and their existence points to moments of unimaginable cosmic force. A star does not simply decide to leave home. To be ejected at speeds exceeding hundreds of thousands of kilometers per hour requires a catastrophic trigger. Astronomers studying M101 have identified several candidate stars whose motion and spectral signatures mark them as likely runaways. The most compelling explanation for their flight is a supernova kick. Imagine a binary system, two stars orbiting one another in a cosmic dance. If one of them is massive, it will live fast, die young, and explode as a supernova. This explosion is not perfectly symmetrical. It can be a lopsided detonation. If the collapsing core of the dying star receives a powerful, one-sided kick at the moment of its death, the entire binary system can be violently disrupted. The surviving companion star, suddenly freed from the gravitational bond with its now vanished partner, is flung away like a stone from a sling, inheriting a tremendous portion of the explosion's recoil energy. It then streaks through interstellar space, a lone traveler on a one-way trip. Another possibility is a gravitational slingshot from a dense cluster. In a crowded stellar nursery, complex gravitational interactions between multiple stars can act like a cosmic pinball machine. A close encounter with a more massive object can transfer enough energy to a smaller star to fling it clear of the cluster entirely, sending it racing into the galactic void. The true value of these runaway stars lies not just in their speed, but in their trajectories. By carefully measuring a runaway star's current position and velocity, astronomers can work backwards, tracing a line across space and time. This path acts as a forensic pointer leading directly back to the scene of the crime. The line may point toward a particular, now quiet region of a spiral arm, hinting at where a supernova occurred millions of years ago. It might lead back to a specific star cluster, identifying it as a site of past gravitational turmoil. Each hypervelocity star is a messenger from a violent event, its very path a clue written in motion. Finding and studying these runaways in the pinwheel allows scientists to map not just where cosmic violence is happening, but where it has already happened, painting a more dynamic history of the galaxy's most energetic moments. The paths of runaway stars are traced by an invisible hand, one that holds the entire galaxy together. This force belongs not to the stars we see, but to a ghostly, unseen presence enveloping the pinwheel. Like all large galaxies, M101 is embedded in a vast, invisible sphere of dark matter. This is not a metaphor, it is a physical necessity. We can map its presence by watching how the galaxy spins. Picture a spiral galaxy like a giant pinwheel toy. If it were made only of the stars and gas we can see, the physics of gravity dictates a specific pattern. Stars close to the bright, dense center should whip around quickly, pulled by the strong gravity there. Stars out in the faint, sparse outskirts should move much more slowly, like the outer edge of a pinwheel lazily turning. But that is not what astronomers observe. When they measure the rotation speeds of stars and hydrogen gas clouds far out in the pinwheel's dim outer reaches, they find something astonishing. Those distant objects are moving just as fast as the stars near the core. The entire galaxy, from its brilliant heart to its faintest edge, rotates like a solid plate. This is impossible if only visible matter is providing the gravity. The only explanation is that the galaxy is immersed in a colossal halo of something else, something that does not emit or reflect light, yet exerts a powerful gravitational pull. This is the dark matter halo. It is the invisible scaffolding upon which the visible galaxy is built, a cosmic framework that contains perhaps 10 times more mass than all the stars and gas combined. We know it is there because of its gravitational signature, but its true nature remains one of the greatest mysteries in all of science. What is it made of? Is it a sea of exotic, undiscovered particles that barely interact with normal matter? Or does it point to a flaw in our understanding of gravity itself? Studying the Pinwheel Galaxy provides crucial clues. By meticulously mapping the rotation curve, the graph of speed versus distance from the center, scientists can infer the shape and density of its dark matter halo. They can ask, is the halo perfectly spherical or is it slightly flattened? How does its density change from the core to the outer darkness? Each detail is a piece of the puzzle. The pinwheel's majestic, well-defined spiral offers a clean laboratory to study this relationship between the seen and the unseen. Its very existence, its ability to hold its shape against the tidal forces of the cosmos, is a testament to the dominant yet invisible hand of dark matter. While dark matter provides the unseen skeleton, the Pinwheel Galaxy's gravitational dance has also sculpted visible, new life from chaos. On the fringes of M101, astronomers have identified two peculiar, faint objects that may be its cosmic offspring. These are tidal dwarf galaxy candidates, and their existence is a direct result of the same gravitational forces that twisted that bright spiral arm. When galaxies have a close encounter, their mutual gravity creates immense tidal forces, much like the moon pulling on Earth's oceans. These tides can become so strong they literally rip long streamers of gas, dust, and stars right out of the galaxy's disks. This stolen material, now flung into intergalactic space, does not simply dissipate. Instead, it can collapse under its own gravity, clumping together to form a brand new small galaxy. This is a tidal dwarf galaxy, a celestial phoenix born from the debris of a galactic interaction. The two candidates near the pinwheel, often labeled as companions in deep surveys, are fascinating because of what they are made of and, crucially, what they lack. Since they formed from the outer disk material of their parent galaxy, they are composed primarily of the same stuff: normal baryonic matter, hydrogen gas, and stars. This makes them surprisingly rich nurseries for new stars. However, because dark matter halos are diffuse and spread out, the tidal forces that formed these dwarfs likely could not pull in a significant amount of that invisible material. Think of it like shaking a bag of mixed nuts and berries. The heavier nuts, representing the stars and gas, might clump together and fall out, while the lighter berry dust, representing the dark matter, mostly stays floating in the air. As a result, these tidal dwarf candidates are believed to be profoundly poor in dark matter. This characteristic makes them exceptional natural laboratories. In the standard model of galaxy formation, dark matter is the essential seed, the gravitational anchor that first draws in normal gas to form stars. A galaxy without a dark matter core challenges that sequence. By studying these objects, scientists can ask fundamental questions. Can a galaxy form and hold itself together through the gravity of its visible matter alone? How does star formation proceed without the deep gravitational well of a dark matter halo? The presence of these candidate dwarfs does more than add two faint smudges to the Pinwheel's family portrait. It offers a rare chance to witness a different path of galactic evolution, one written not in the dark, but in the luminous aftermath of a gravitational storm. But even the formation of new galaxies pales next to the drama of a single star's death throes. Within one of the Pinwheel's spiral arms, a star designated as M101WR is writing its final chapter in fire and fury. This is no ordinary sun. It is a Wolf-Rayet star, a member of one of the rarest and most extreme stellar classes in the universe. Imagine a star that began its life with a mass dozens of times greater than our sun. It has burned through its nuclear fuel at a frantic, profligate pace, living a short and violent life. Now, in its final millennia, it has peeled itself bare. Powerful radiation pressure from its searing hot core has blasted away its outer layers of hydrogen and even helium, revealing a naked, ferocious furnace of heavier elements like carbon, nitrogen, and oxygen. What remains is a stellar core exposed to the void, screaming its existence into space with a hurricane-force wind. The star M101WR is not just a Wolf-Rayet star, it is an episodic one. Its behavior is erratic and unpredictable. For periods of time, it might maintain a steady, albeit immense, output of light and stellar wind. Then, without clear warning, it can erupt. Its brightness might fluctuate wildly, and the speed and density of the material it blows into space can change dramatically. It is a star having violent, periodic fits. This episodic nature makes it a priceless real-time laboratory. Astronomers are essentially watching a star in its final act, a preview of a coming supernova. The unpredictable changes in mass loss are critical clues. They tell scientists about the instabilities deep within the star's core as it fuses ever heavier elements, inching toward the moment of catastrophic collapse. Each great belch of material is like a seismic tremor before a volcanic eruption, a sign of the tremendous pressures building inside. By studying the chemistry of the winds, they can see what elements are being forged in these final moments. By measuring the changes in brightness, they can model the structural changes in the star itself. This star is a clock, but one whose ticking is irregular and accelerating. Its very unpredictability is the key data. Will its next great episode be its last? Could a sudden, massive ejection of material be the prelude to the final collapse? Watching this episodic Wolf-Rayet star is as close as we can get to staring at a supernova countdown clock, one that reminds us that even the most colossal structures in the cosmos are governed by the unstable, dying breaths of their constituent stars. That dying star's ferocious winds are not the only unseen force shaping the galaxy. some of the pinwheel's most energetic processes hide behind a veil of dust, revealing themselves only in a whisper of warmth. Telescopes like the Spitzer Space Telescope, designed to see the universe in infrared light, have pinpointed regions within M101 that blaze with an intense, mysterious heat signature. These are unidentified infrared emitters, cosmic hotspots that glow brightly in the long wavelengths of infrared radiation, but remain faint or invisible in the optical light our eyes can see. Infrared light is essentially the glow of heat. When you feel the warmth radiating from a stovetop element that's still hot but no longer glowing red, you are sensing its infrared emission. In space, vast clouds of cosmic dust made of tiny silicate and carbon grains are excellent at absorbing the visible light from young, hot stars. This dust doesn't let that light pass through. It soaks it up, heats up like sand on a sunny day, and then re-radiates the energy back out as infrared warmth. So, an intense, unresolved infrared source is a beacon pointing to something hidden. One compelling explanation is a massively obscured stellar nursery. We could be looking at a region where star formation is occurring at a frantic, almost violent rate, but it is all happening deep inside an incredibly thick cocoon of gas and dust. The brilliant blue light of countless newborn massive stars is completely trapped, their visible glory converted into a diffuse, warm infrared glow. It's a stellar factory operating behind blackout curtains. Another possibility ties back to the galaxy's turbulent history. This intense infrared emission could be the thermal echo of a recent merger or a very close gravitational encounter with a smaller galaxy. The collision would have sent shock waves through the galactic gas, compressing it suddenly and triggering a burst of star formation so intense and so shrouded in the debris of the impact that it only announces itself in this heated whisper. There's also a chance it represents an unusual type of nebula, perhaps one energized not by young stars but by the remnant of a dead one, like a pulsar wind nebula, where a rapidly spinning neutron star blows a bubble of energetic particles into surrounding dust, heating it from within. The unidentified label is crucial. It means that while we can detect the heat, we cannot yet definitively see what the furnace looks like or what is stoking the fire. This infrared mystery is a reminder that our view of the cosmos, even in a relatively nearby galaxy, is profoundly limited by the tools we use to see. What looks like a quiet patch of darkness in an optical image might, in the infrared, be the site of the most tumultuous and hidden event in the entire spiral arm. These hidden furnaces of infrared light remind us that seeing is not always believing in the cosmos. To truly map the universe, astronomers rely on trusted guides, stars whose behavior is so predictable they act as cosmic lighthouses. Among the most crucial are the Cepheid variables, pulsating stars that rhythmically brighten and dim over days or weeks. Their magic lies in a tight, dependable relationship between their pulsation period and their true intrinsic brightness. A Cepheid that takes 10 days to complete one pulse cycle is always, in theory, exactly 100 times more luminous than one with a one-day period. By measuring how long it takes to pulse and comparing its apparent brightness from Earth, astronomers can calculate its distance with remarkable precision. These stars built the cosmic distance ladder, allowing us to measure the scale of our galaxy and beyond. Yet in the Pinwheel Galaxy, some of these trusted guides are starting to misbehave. Astronomers have identified Cepheids within M101 whose pulsations are erratic or whose brightness does not match the expected pattern for their period. They are the anomalous Cepheid variables, and their existence throws a wrench into our most fundamental tool for cosmic cartography. What could cause such a reliable star to go off script? One possibility involves the star's chemical makeup. Cepheids are typically divided into two populations. Classical Cepheids are young, massive stars found in spiral arms, rich in heavier elements. Type II Cepheids are older, lower-mass stars often found in galactic halos with fewer of these metals. the period luminosity relationship is slightly different for each type. If a Cepheids in the pinwheel has an unusual blend of elements, perhaps from forming in a region enriched by prior supernova, its internal structure and pulsation physics could be altered, making it appear too bright or too dim for its clockwork rhythm. Another, more intriguing idea is binarity. What if the Cepheids is not alone? If it has a faint, close companion star, the combined light from the two could fool our measurements, making the Cepheids seem brighter than it truly is and thus throwing off the distance calculation. Or the gravitational tug of a companion could subtly influence the pulsation timing itself, creating a wobble in the rhythm. Each anomalous Cepheids is a problem that demands a solution because the stakes are universe-sized. If our standard candles are not perfectly standard, then every rung on the distance ladder becomes slightly less certain. This affects our measurement of the Hubble constant, the rate of the universe's expansion, and therefore our understanding of cosmic history and destiny. The Pinwheel Galaxy, by presenting these flawed lighthouses, is not just being difficult. It is forcing astronomers to scrutinize their most trusted tools, to clean the cosmic lenses, and to build a more robust and nuanced map of everything. The reliability of our cosmic lighthouses is challenged by something far more energetic, a signal screaming across the radio spectrum. Among the many glowing clouds of the Pinwheel Galaxy, one stands out not for its visible beauty but for a powerful, invisible voice. This is a radio-loud H2 region, a cosmic anomaly where a familiar stellar nursery broadcasts an unexpected signal. To understand why this is so strange, we first need to know what a normal H2 region is. The H2 stands for molecular hydrogen, the basic fuel of the universe. When a young, massive star ignites, its intense ultraviolet radiation blasts the surrounding cloud of cold hydrogen gas. This radiation strips electrons from the hydrogen atoms, a process called ionization, and heats the gas to thousands of degrees. The result is a brilliant, glowing nebula, like the famous Orion Nebula in our own sky. These regions are optical powerhouses, shining in beautiful reds and pinks from the recombination of electrons and protons. They are the visible cradles of star birth. But in M101, astronomers have found an H2 region that breaks the mold. While it certainly emits visible light, its most striking feature is an intense, dominant roar of radio waves. This is highly unusual. Typical H2 regions are relatively quiet in the radio band, their emission coming from a gentle thermal process related to the hot gas. The radio-loud region in the pinwheel, however, is anything but gentle. Its radio signature is strong and broad, the kind usually associated with violent, non-thermal processes. Something within that cloud of newborn stars is generating a tremendous amount of synchrotron radiation, the same kind of emission produced when high-speed electrons spiral around magnetic field lines. So what hidden engine could be powering this radio shout from a stellar nursery? One leading suspect is an embedded supernova remnant. Imagine that within this glowing cloud, a massive star has already lived its short life and exploded. The expanding shell of debris from that ancient supernova, plowing through the surrounding gas at supersonic speeds, would generate powerful shock waves. These shocks can accelerate electrons to near light speed, creating a brilliant source of synchrotron radio emission that would completely overshadow the gentle thermal radio glow of the H2 region itself. It would be like hearing a jet engine roar from inside a choir rehearsal. Another fascinating possibility is a microquasar. This is a stellar mass black hole or neutron star actively feeding on a companion star, mimicking the behavior of a distant quasar but on a tiny scale. Such an object can launch powerful, focused jets of material that slam into the surrounding nebula gas. The collision point where the jet meets the cloud becomes a brilliant hotspot of radio emission. A single microquasar hidden in the cloud could easily explain the intense, localized radio signal. A third explanation points to the stars themselves, but of an extreme variety. Perhaps this region is home to an unusually high concentration of the most massive O-type stars or even Wolf-Rayet stars. These stellar behemoths don't just shine, they blast their surroundings with hurricane-force stellar winds, moving at thousands of kilometers per second. The collision of multiple, powerful stellar winds within the confined space of the nebula could create chaotic shock fronts, again accelerating particles and generating strong synchrotron radio noise. This radio-loud region transforms a simple picture of star birth into a scene of layered history and hidden violence. It tells us that within what looks like a peaceful stellar nursery, there may lie the corpse of a dead star, the fury of a hidden black hole, or the collective scream of stellar hurricanes. The cloud is not just giving birth to stars, it is broadcasting the energetic consequences of their lives and deaths on a frequency we are only just learning to hear. That radio signal emerges from a sea of gas far larger than the galaxy's starlight reveals. Surrounding the brilliant spiral of M101 is an immense, faint ocean of neutral hydrogen gas, a disk that stretches far beyond the last visible stars. This is the galaxy's true extended atmosphere, a reservoir of raw material for future generations of suns. But recent radio telescope observations have uncovered a startling fact about this vast disk. It is not flat and pristine. Instead, it is profoundly warped, twisted out of shape like a vinyl record left too long in the sun. The pinwheel's foundational gas layer is bent. This warping is not a minor flaw, it is a major distortion in the galaxy's fundamental structure. Neutral hydrogen gas is famously difficult to see in visible light, but it broadcasts a clear signal at a specific radio wavelength, 21 centimeters, a signature that radio telescopes like the Very Large Array can map with exquisite detail. These maps show the gas disk flaring and twisting at its outer edges, with entire sections lifted above or pushed below the galaxy's central plane. It is a cosmic wobble frozen in time. So what immense force could bend a structure of such staggering scale? Astronomers point to three compelling suspects. The first is an ongoing gravitational tug of war with the Pinwheel satellite galaxies. We know M101 has smaller companion galaxies dancing around it, bound by its gravity. Even if a dwarf galaxy passed by millions of years ago without a direct collision, its persistent gravitational pull, like a constant hand tugging on a tablecloth, could gradually warp the extended, delicate gas disk over cosmic time. The second possibility is intergalactic gas accretion. The pinwheel is not floating in a perfect void. It moves through the thin, hot plasma that fills the space between galaxy clusters, known as the intergalactic medium. If the galaxy is plowing through a denser filament of this primordial gas, the resulting pressure, like the bow wave of a ship, could push and distort the leading edge of its hydrogen disk, bending it backward. The third, and perhaps most profound, explanation involves the invisible architecture we discussed earlier, the dark matter halo. We assume this halo is roughly spherical, but what if it isn't? If the dark matter distribution is itself lopsided or triaxial, its gravitational pull would be uneven. The visible stars, held tightly together, might not feel this subtle imbalance as strongly, but the vast, tenuous cloud of hydrogen gas extending far out into the halo would be exquisitely sensitive to it. The warp in the gas could be a direct map, a shadow, of an invisible and asymmetric dark matter skeleton. This bent hydrogen disk is more than a curiosity. It is a dynamic record of the forces acting upon the galaxy. It tells us the pinwheel is not an isolated island universe, but an active participant in a cosmic environment, constantly shaped by interactions both seen and unseen. The very fuel for its future is being stirred by ghosts from its past and present. The warped hydrogen disk hints at hidden structures, and within one of the pinwheel's massive star clusters, astronomers may have found the ultimate hidden object. This is the search for the candidate intermediate mass black hole, a cosmic missing link that could rewrite our understanding of how the universe builds its most terrifying giants. We know of two main classes of black holes. Stellar mass black holes, up to a few dozen times the Sun's mass, are the corpses of massive stars. At the other extreme, supermassive black holes, millions to billions of solar masses, anchor the centers of galaxies. But what lies between? For decades, the intermediate mass black hole, weighing between 100 and 100,000 solar masses, has been a theoretical ghost. Finding one would bridge the gap, showing how the small could grow into the monstrous. The Pinwheel Galaxy offers a prime hunting ground. Deep within a particularly dense and ancient globular cluster, a swarm of hundreds of thousands of stars gravitationally bound together. Data from X-ray observatories like Chandra and optical telescopes have revealed tantalizing clues. At the cluster's heart, there is a persistent, bright source of X-rays. This emission is too powerful to be explained by a collection of ordinary stellar remnants like neutron stars. Furthermore, the motion of stars at the cluster's core, measured by their subtle Doppler shifts, suggests they are whipping around faster than expected. They seem to be orbiting an invisible, concentrated mass. Put these pieces together, and the picture points to a single, dark object with a gravitational pull equivalent to thousands of suns, a strong candidate for an intermediate mass black hole. Why would such an object form here? One theory is that it grew over eons through countless mergers of smaller black holes and stars within the dense cluster core, a slow-motion game of gravitational pinball where the biggest object always wins. Another idea is that it is the stripped core of a dwarf galaxy that the pinwheel consumed long ago, its central black hole left wandering within the star cluster as a cosmic trophy. Confirming this candidate would be a landmark achievement. It would validate a key prediction of black hole evolution and provide a living example of how supermassive black holes might have taken their first steps, growing from these intermediate seeds. It would also transform our view of these ancient star clusters from simple stellar retirement homes into dynamic arenas where black holes can form and grow. The hunt in the pinwheel is a meticulous process of elimination, ruling out every other possibility until only one extraordinary explanation remains. The hunt for a hidden black hole unfolds within a galaxy already sculpted by titanic forces on a far grander scale. If we pull our view back from individual clusters and stars, we see the Pinwheel Galaxy's spiral arms are not just ribbons of light, but landscapes etched with colossal voids. These are superbubbles, some of the largest structures any single galaxy can create. Picture not a bubble from a child's wand, but a cavern in space, a spherical cavity that could swallow our entire solar system thousands of times over, stretching hundreds of light years from wall to wall. In M101, these superbubbles are not rare. They form vast complexes, interconnected networks of emptiness that define the anatomy of its spiral arms. They are the aftermath of a specific kind of violence, not a single explosion, but a sustained, coordinated assault on the interstellar medium. Their creation begins with a stellar association, a family of dozens of the most massive O-type and Wolf-Rayet stars, all born from the same giant cloud roughly at the same time. Each of these stars is a powerhouse, emitting a relentless hurricane of charged particles, a stellar wind moving at millions of kilometers per hour. For millions of years, these winds carve away at the surrounding gas, pushing it outward and creating a growing cavity. Then, the eldest of these massive stars begin to die. One by one, they explode as supernova. Each detonation delivers a seismic shockwave that slams into the walls of the cavity, expanding it further and heating the gas to extreme temperatures. The combined effect of these sequential winds and explosions is a cosmic excavation project of unimaginable scale, hollowing out a superbubble. But these structures are far more than just empty space. They are dynamic engines that drive the galaxy's evolution. The gas on the inner surface of the bubble, heated to millions of degrees by the supernova shocks, begins to glow intensely in X-rays, creating a brilliant, thin shell we can detect with space telescopes. More importantly, as the bubble expands, the pressure inside becomes tremendous. Eventually, the weakest point of the spherical shell, often the top and bottom relative to the galaxy's disk, ruptures. When this happens, the hot, metal-rich gas from inside the bubble erupts outward, not just into the galactic disk, but perpendicular to it, shooting fountains of material far above and below the plane of the galaxy. These are the galactic chimneys. They function exactly like a fireplace chimney, venting the energetic byproducts of stellar life and death out of the star-forming disk. This process is crucial for the galactic ecosystem. The material blown out is not just hot, it is chemically enriched. It carries the heavy elements forged in the cores of those massive stars and dispersed in their supernova explosions, elements like oxygen, silicon, and iron, the very building blocks of rocky planets and life itself. Through these chimneys, the superbubble complex in the Pinwheel Galaxy is actively polluting intergalactic space, seeding the void with the processed remains of stars. This cycle regulates the galaxy itself. By blowing gas and energy out, it can actually shut down further star formation in that region by dispersing the raw fuel. Yet, that ejected material may eventually cool, fall back down in a galactic rain, and trigger new rounds of star formation elsewhere. The superbubble is both a destroyer and a creator, a testament to how the collective lives and deaths of stars don't just light up a galaxy, but architect its very structure and future. These galactic chimneys are forged by stars living on the very edge of stability, and in the pinwheel we can watch one such star teetering on the brink. Within its spiral arms lies a luminous blue variable, a stellar behemoth in the final, most volatile chapter of its life. This class of star represents a brief, violent transition phase for the most massive suns, those born with over 50 times the mass of our own. They are cosmic pressure cookers, where the outward radiation pressure from the furious nuclear fusion in the core battles so intensely against the inward pull of gravity that the star cannot maintain a stable form. It becomes seismically unstable, prone to colossal eruptions that can reshape its entire appearance. Astronomers have captured direct evidence of one such eruption in M101. Over a period of months, this particular LBV underwent a dramatic transformation. Its brightness surged, increasing by a factor of 10 or more, as if a cosmic switch had been flipped. This was not a slow, steady change, but a violent outburst. The star did not explode. Instead, it violently ejected a significant portion of its own outer layers into space. Imagine a giant, gaseous star having a catastrophic temper tantrum, blowing off a shell of material equivalent to the mass of several planets or even a small star. This expelled gas forms a temporary, expanding nebula around the star, a glowing shroud that eventually dissipates. Studying this event in the pinwheel is like having a front row seat to a dress rehearsal for one of the most anticipated stellar spectacles in our own galaxy, the eventual fate of Eta Carinae. That star in our Milky Way is the closest and most famous luminous blue variable. In the 1840s, it underwent a similar, massive eruption, becoming for a time the second brightest star in the night sky and ejecting the famous homunculus nebula. By observing the LBV in M101, scientists can compare the mechanics of its eruption, the composition of the ejected material, and the star's recovery. They ask critical questions. What triggers these outbursts? Is it a buildup of radiation pressure that finally blows a valve? Does it involve deep structural changes as the star fuses new elements in its core? Each observation helps refine models that predict not just when, but how Eta Carinae will finally meet its end. The Pinwheel's LBV is a crucial case study, a distant warning flare that illuminates the chaotic and spectacular final years of the universe's most massive stars, reminding us that their death is often a long, turbulent process, not a single, sudden event. That volatile star's eruptions are just one way the galaxy replenishes itself from within, but a more fundamental source of fuel arrives from the great emptiness beyond. The Pinwheel Galaxy is not a closed system, it is actively feeding. Radio telescopes have mapped vast clouds of cool, neutral hydrogen gas screaming toward the galaxy's disk at astonishing speeds, hundreds of kilometers per second. This is not gas gently circulating within the spiral. This is a high-velocity cloud infall, a cosmic downpour of raw material plummeting from intergalactic space. Picture a galaxy not as an island, but as a gravitational whirlpool in an ocean of thinly spread matter. These massive, cool clouds, each containing enough gas to form millions of stars, are caught in the galaxy's pull. They streak inward, often on angled trajectories, destined to slam into the outer galactic disk. This process, called galactic accretion, is the primary way a mature spiral galaxy like M101 gathers the fuel for its future. Without this fresh influx of hydrogen, the galaxy would eventually starve itself. It would convert all its available gas into stars, and with no new fuel, star formation would sputter and cease. The brilliant spiral arms would dim as the massive, short-lived stars died out, leaving behind only older, redder stars. The high-velocity infall is what keeps the pinwheel alive and vibrant, constantly topping up its gas tank to birth new generations of suns. But this crucial process raises a profound mystery. Where do these immense, fast-moving clouds originate? Astronomers are investigating two compelling and very different possibilities. The first idea is that they are primordial leftovers, ancient filaments of gas that never fully collapsed into galaxies during the universe's formative epochs. These clouds would be fossils from the dawn of time, composed almost purely of hydrogen and helium, the pristine elements forged in the Big Bang. They have been wandering the cosmic voids for billions of years, only now being captured by the pinwheel's growing gravitational influence. The second possibility tells a story of galactic cannibalism. These clouds may not be pristine at all, but the shredded remains of smaller dwarf galaxies that ventured too close. As a dwarf galaxy is torn apart by the pinwheel's tidal forces, its stars may be scattered, but its diffused gas can be stretched into long, streaming filaments that eventually fall back onto the larger galaxy as high-velocity clouds. This material would be slightly enriched with heavier elements from the dwarf galaxy's own stellar generations. Determining the origin is more than academic. It changes the narrative of the galaxy's growth. Is the pinwheel gently gathering untouched cosmic dew, or is it feasting on the dismembered gas of its former companions? Each new cloud detected, with its specific speed, trajectory, and chemical signature, is a clue to a deeper history, revealing whether the galaxy builds itself from the virgin material of the cosmos or from the recycled ashes of its neighbors. This galactic feeding grounds the very star clusters that define its ancient history, yet some of those clusters defy expectation. Scattered throughout the halo of the Pinwheel Galaxy are dense, spherical swarms of stars known as globular clusters. These are normally the graybeards of a galaxy, ancient relics that formed in its earliest, violent days over 10 billion years ago. Their stars are typically old, cool, and yellow, having long ago burned through their fast-burning blue giants. This gives most globular clusters a characteristic golden hue, but in M101, a curious population stands out. Several of these clusters appear anomalously, strikingly red. This is not a trick of the light or a photographic effect. Their color, measured precisely through filters, is redder than the standard ancient cluster should be. This crimson tint presents a stellar mystery with several compelling solutions. The first theory challenges the very age of these objects. Perhaps they are not ancient at all. Could they be younger globular clusters formed more recently in the pinwheel's dynamic history? If they are only, say, a few billion years old instead of over 10, they might still contain a significant population of red giant stars. These are elderly stars in a late, bloated phase that glow with a distinct reddish light. A cluster rich in red giants would skew the entire swarm's color toward the red end of the spectrum. This would be a major discovery, as it suggests the pinwheel had a later, secondary wave of globular cluster formation, something not seen in many other galaxies. The second theory focuses on chemistry. The color of a star is deeply tied to its chemical composition, specifically its metallicity, which in astronomy means the abundance of elements heavier than hydrogen and helium. Stars with higher metallicity, more of these heavier elements, tend to be redder and cooler. So, these red clusters might be ancient, but they formed from gas that was already unusually enriched with metals from earlier generations of supernova. They would be cosmic aristocrats born with a silver spoon, their stellar composition fundamentally different from the pristine, metal-poor clusters we usually see. A third, more straightforward idea is simple obstruction. What if the clusters themselves are not intrinsically red, but are just being made to look that way? Vast lanes of interstellar dust drift within the pinwheel's disk and halo. This dust is excellent at scattering and absorbing blue light, while allowing redder light to pass through more easily, the same effect that gives us red sunsets on Earth. If a significant cloud of this dust lies along our line of sight to a cluster, it would act like a reddish filter, making a normally golden cluster appear ruddy. Determining which theory is correct requires peeling back the layers of the mystery. Astronomers use spectroscopy to analyze the light from individual stars within these red clusters, looking for the signatures of age and metallicity. They also map the dust distribution across the galaxy. Each red globular cluster is a time capsule, but one that sends a mixed message. Is it a younger imposter among the ancients, a chemically distinct relic, or simply an old cluster wearing a veil of cosmic dust? Their unusual color is a quiet but persistent question about the pinwheel's unique evolutionary path. The red clusters speak of a quiet history, but the Pinwheel Galaxy also broadcasts sudden, brilliant alarms. Among its catalog of X-ray sources, one stands out for its strange and fleeting nature. Astronomers detected a point of light that pulsed with a rapid, steady rhythm, a cosmic heartbeat beating in the high-energy language of X-rays. This was no ordinary pulsar. It was a transient anomalous X-ray pulsar candidate, and its most peculiar feature was that it did not last. Over weeks and months, this pulsing beacon gradually faded, dimming until it vanished back into the background noise of the galaxy. This behavior is the signature of a specific and terrifying breed of stellar corpse, a magnetar in outburst. To understand a magnetar, first picture a neutron star, the collapsed core of a massive star after a supernova. It is a city-sized sphere of pure, degenerate matter, so dense that a single sugar cube-sized piece would weigh as much as a mountain. Now, take that incredible object and imbue it with the most powerful magnetic field known to exist in the universe. A magnetar's magnetic field is a quadrillion times stronger than Earth's, and 1,000 times stronger than a typical neutron star's. This field is so unimaginably intense that it strains the very fabric of the star itself. The crust of the neutron star, a lattice of iron nuclei, is under constant, unbearable stress. Occasionally, this crust can crack, like the tectonic plates of a world under impossible pressure. When it does, it releases a starquake, a seismic event of cosmic proportions. The energy released in that fracture is staggering, flooding the surrounding space with a burst of X-rays and gamma rays. This is what astronomers believe they witnessed in the pinwheel, a magnetar's crust snapping and unleashing its pent-up fury. The initial detection of the rapid pulses was the magnetar's lighthouse beam sweeping past us as it spun. The gradual fading was the aftermath of the quake, the hot, energized surface of the star slowly cooling down as the violent event subsided. Catching such an object in the act is extraordinarily rare. Magnetars themselves are uncommon, with only a few dozen confirmed in our entire Milky Way. To see one during its brief, violent outburst in another galaxy is a stroke of immense luck. It is like witnessing a specific, distant volcano erupt on a single day across an ocean of stars. The value of this observation is profound. It gives scientists a pristine laboratory to study the physics of matter under conditions impossible to replicate on Earth, at magnetic field strengths that defy comprehension. By watching the pulse rate and the cooling curve, they can probe the internal structure of the neutron star, estimate the thickness of its crust, and measure the unbelievable strength of the magnetic field that powers its apocalyptic tantrums. This transient pulse, now silent, leaves behind crucial data, a fingerprint of the most magnetic objects in the cosmos. The fading heartbeat of that magnetar leaves a faint, lingering energy in the galactic void, but it is not the only source of invisible light. Enveloping the entire Pinwheel Galaxy, far above and below its bright starry disk, is a vast and ghostly atmosphere. This is the diffuse ionized gas halo, often called the DIG, a tenuous ocean of superheated hydrogen that glows with a faint, pervasive red light. If you could see the galaxy in the specific wavelength emitted by ionized hydrogen, it would appear not as a flat spiral, but as a luminous, softly glowing egg with the familiar disk embedded at its center. This is the galaxy's true extended atmosphere, a structure that has long puzzled astronomers because of a simple, persistent question: what is keeping it so hot? Ionization requires energy. To strip an electron from a hydrogen atom takes a powerful jolt, typically from a high-energy ultraviolet photon. Within the disk, the source is obvious, the brilliant light from massive young stars in nebulae. But the DIG halo extends thousands of light years beyond these stellar nurseries, into regions where there are very few, if any, such stars. The energy source here is hidden, a galaxy-wide mystery. Scientists have proposed several candidates to explain this pervasive heating. The first is radiation leakage. Perhaps enough high-energy photons are escaping the galactic disk, like light leaking from a cracked door, to weakly ionize the distant gas. The second involves the galactic chimneys we discussed earlier. Those superbubbles vent hot, metal-rich gas from the disk, and this fountain of material could rise, cool, and mix with the halo, transferring energy and helping to sustain the ionization. A third, more dramatic idea points to shock waves rippling through the halo. These could be generated by continual minor mergers with tiny satellite galaxies or by the infall of those high-velocity gas clouds, their impact sending tremors through the thin atmospheric gas. But there is a fourth and far more exotic possibility. Some theorists have suggested the energy might not come from stars at all, but from the invisible fabric of the galaxy itself. Could it be the decay of dark matter particles? If the mysterious substance that makes up the dark matter halo is not perfectly stable, but slowly decays into standard particles, that process would release a faint, uniform drizzle of energy across the entire halo. This energy could be just enough to keep the diffuse gas ionized. The DIG halo, therefore, is more than a pretty glow. It is a calorimeter, a galaxy-sized device measuring the total energy budget from all sources, both seen and unseen. By mapping its brightness, temperature, and structure, astronomers are essentially taking the temperature of the pinwheel's hidden energy flows, searching for clues to a power source that operates on a scale larger than anything its visible stars could provide alone. That ghostly halo is a whisper of the galaxy's past, but its very heart holds a more tangible clue to a violent history. At the very core of the Pinwheel Galaxy, where we expected a quiet center, astronomers have found something else entirely. Observations suggest the dense nuclear star cluster, the tight swarm of ancient suns orbiting the galactic midpoint, is tilted. It appears to be rotating on a different plane than the main galactic disk. This is not a minor misalignment. It is as if the galaxy's central jewel is set at a crooked angle, spinning to a rhythm all its own. Such a profound tilt is not something that happens by chance in an isolated, peaceful galaxy. The most compelling explanation points to a cataclysmic event in the distant past, a galactic merger. Picture this scenario. Billions of years ago, a smaller galaxy, perhaps a dwarf spiral or an irregular galaxy, was on a collision course with the proto-pinwheel. It did not hit head-on but came in at an angle. As the two galaxies merged, their stars and dark matter halos would eventually mix, blurring into a single, larger system that settled into the beautiful spiral we see today. But the core of the swallowed galaxy, its dense nuclear star cluster, is stubborn. Held together by its own intense gravity, it would resist being completely torn apart. Instead of dissolving, it could have survived largely intact, sinking through the merger debris toward the new combined center of gravity. However, it would have brought its original spin direction with it. So, what we see today as the tilted nuclear cluster may be the preserved core of that devoured galaxy, a fossilized record of its original orientation, now forever askew within its conqueror's belly. This discovery transforms the quiet center from a simple mystery into a dynamic crime scene. The tilted cluster is a gravitational fingerprint, evidence left behind from a cosmic act of cannibalism. It tells us the Pinwheel Galaxy did not form in serene isolation. Its majestic spiral arms and vast disk were forged, at least in part, from the shredded remains of another galactic system. This tilted heart challenges the idea of galaxies as island universes, painting them instead as evolving structures built from successive mergers, each event leaving its own unique mark on the final form. The next time you see an image of the pinwheel's perfect face, remember, its beautiful symmetry hides a core spinning to the beat of a different and far more ancient drummer. A tilted core hints at a galactic feast, but the meal may have been smaller than expected. The Pinwheel Galaxy, like our own Milky Way, presents astronomers with a profound and persistent cosmological puzzle known as the missing satellite problem. Sophisticated computer simulations of how structure forms in a universe filled with dark matter predict a very specific outcome. A grand spiral galaxy like M101, with its immense dark matter halo, should be surrounded by a bustling swarm of hundreds, if not thousands, of smaller dwarf satellite galaxies. These would be the cosmic equivalents of moons orbiting a planet, held in place by the larger galaxy's gravitational dominance. Yet when we look, the reality is starkly different. We see only a handful. The Pinwheel's known satellite system is sparse, with just a few confirmed dwarf galaxies like its companions NGC 5474 and NGC 5477. The vast majority of predicted satellites are simply not there. This isn't just an observational shortcoming. It's a direct clash between our best theoretical models of cosmic evolution and the actual universe we see. So where did all the missing dwarfs go? One leading theory suggests they were never there to begin with because of the very nature of dark matter. The simulations that predict hundreds of satellites are based on the idea that dark matter is cold and collisionless, meaning the particles move slowly and mostly pass right through each other and normal matter. This allows it to clump easily into many small halos early in the universe, which should then attract gas and form small galaxies. But what if dark matter is slightly warmer? If the hypothetical particles moved faster in the early universe, they would have had more energy, making it harder for them to collapse into the tiniest clumps. This warm dark matter scenario would naturally produce far fewer small dark matter halos, and thus far fewer dwarf galaxies from the start. The missing satellites might be missing because the seeds for them never formed. Another possibility is that the seeds were there, but the galaxies never sprouted. Reionization, a pivotal epoch a few 100 million years after the Big Bang when the first stars flooded the universe with intense ultraviolet radiation, could be the culprit. This global bath of energetic photons could have heated the gas within the smallest, most vulnerable dark matter halos, preventing it from cooling, condensing, and forming stars. These halos would remain as dark, starless ghosts invisible to our telescopes, but still present as lumps of pure dark matter orbiting the pinwheel. We wouldn't see them, but they would still exert a gravitational tug. A third, more violent explanation is that the satellites did form but were destroyed. The intense tidal forces and radiation from the growing Pinwheel Galaxy could have stripped away their gas and even torn apart their stars, dissolving them into faint stellar streams that now blend imperceptibly into the galactic halo. The sparse satellite system we observe today might be the hardy survivors of a much larger population that was systematically dismantled over billions of years. The pinwheel's quiet neighborhood, therefore, is not evidence of a peaceful past but a potential crime scene. Its missing satellites force us to question the fundamental properties of the universe's dominant ingredient, dark matter, and to reconsider the harsh, unforgiving environment of the early cosmos where only the strongest small galaxies could endure. That sparse satellite system speaks to a galaxy that grew alone, yet its chemical makeup tells a different story of deep internal mixing. The Pinwheel Galaxy possesses an anomalous metallicity gradient, a subtle but crucial clue written in the very atoms of its stars. In astronomy, metals refers to any element heavier than hydrogen and helium. When we map a typical spiral galaxy, we find a clear and predictable pattern. The central regions, dense with ancient stars and the repeated ashes of supernova, are rich in these heavy elements. As you move outward along the spiral arms, the metallicity steadily declines. The outskirts are more pristine, composed of gas that has undergone less stellar processing. It is a cosmic fingerprint of a galaxy that formed from the inside out. M101 breaks this rule. Detailed spectroscopic studies of its stars and nebulae reveal a gradient that is surprisingly flat or even complex and wavy. The decline in metallicity from the core to the far edges is not as steep as models predict. In some regions of the outer disk, the metal content is higher than it should be. This is not a minor discrepancy. It is evidence that the galaxy's ingredients have been thoroughly stirred. Something has been churning the galactic pot, transporting metal-rich gas from the busy inner zones out into the galactic suburbs. The most powerful mixer is the galactic fountain process, driven by those superbubbles and chimneys we explored earlier. When massive star clusters die in spectacular successive supernova, they do not just carve cavities, they launch fountains of hot, enriched gas high above the disk. This material, laden with iron, oxygen, and silicon forged in stellar furnaces, eventually cools and condenses. It then rains back down onto the disk, but not necessarily in the same place. Like a weather system, this metal-rich rain can fall far from its origin, seeding distant spiral arms with elements that should not, under calm conditions, be there. This process creates a more homogeneous chemical mix, flattening the expected gradient, but the galactic fountain might not be the only chef in the kitchen. The flatter gradient could also be a lasting signature of the galaxy's merger history. If the pinwheel indeed consumed a smaller companion galaxy billions of years ago, the violent act of merging would have been incredibly efficient at stirring the two systems' gases together. The gravitational turbulence would have scrambled the once separate chemical reservoirs, blending enriched and pristine gas across a vast area. The final galaxy would bear a more uniform metallicity as a relic of that ancient chaos. A third possibility involves the steady accretion of those high-velocity gas clouds. If the incoming clouds are not pristine, but are themselves slightly enriched from their own past star formation, they would be depositing heavier elements directly into the outer disk as they fall, propping up the metallicity in the regions where it should be lowest. This anomalous gradient forces us to see the galaxy not as a static painting, but as a dynamic, simmering cauldron. Its chemistry is a palimpsest, a document written over many times by winds, explosions, mergers, and cosmic rain. The unexpected presence of metals in its far reaches is a quiet testament to the energetic processes that have been shaping its destiny for eons, blurring the lines between its core and its frontier. These chemical whispers from the galactic disk lead us to a single, peculiar star that may be hiding a monstrous secret. Among the countless suns in the pinwheel, one stands out not for its brightness but for its bizarre composition. It possesses an overabundance of lithium, rubidium, and molybdenum, elements that are normally scarce and destroyed in the nuclear furnaces of typical giant stars. This strange chemical fingerprint has led some astronomers to propose a breathtaking possibility that this star is a candidate Thorn-Zitkow object. The very name sounds like science fiction, and the reality is perhaps even stranger. A Thorn-Zitkow object is a theoretical stellar hybrid, a cosmic chimera. Picture a red supergiant star, a vast, bloated sphere of cool gas so enormous it could engulf the orbit of Jupiter. Now, imagine that instead of a conventional nuclear fusion core at its heart, there is something utterly different, a city-sized neutron star. This is not a binary system where two stars orbit each other. This is a single star with a neutron star as its engine. Theorists Kip Thorne and Anna Zitkow proposed that such a freak of nature could form from a rare and violent dance. In a dense binary system, a neutron star, the remnant of a supernova, could spiral into the envelope of its expanding giant companion. Instead of being ejected or causing a cataclysm, the neutron star would sink to the center, displacing the giant's core. The result is a star within a star. The outer layers are the puffy, cool hydrogen of the red giant. The power source is the immense gravitational energy and heat released as matter from the giant's innards rains down onto the surface of the ultra-dense neutron star at its core. This exotic setup is predicted to produce a very specific pattern of elements. The intense, neutron-rich environment around the core would foster unusual nuclear reactions, a process called the slow neutron capture process, which steadily builds up heavier elements like rubidium and molybdenum. It would also miraculously preserve lithium, an element usually quickly burned in stellar interiors. The star in M101 shows these exact signatures. If confirmed, it would be the first Thorn-Zitkow object ever identified, a living fossil from a stellar merger that defies ordinary classification. It would be a direct window into extreme nuclear physics operating inside a truly unique environment. The candidate star is a cosmic question mark, a single point of light that could validate a decades-old theoretical prediction and reveal an entirely new way for stars to live and ultimately to die. That chemical anomaly points to hidden stellar violence, but the final mystery of the Pinwheel Galaxy is a flash of light without a name. In 2004, a brilliant point of light emerged in one of its spiral arms where no star had been catalogued before. It grew steadily brighter over several weeks, captured by automated sky surveys, and then, just as steadily, it faded back into the darkness. It was an optical transient, a temporary visitor in the sky, but this one carried no identification. It did not fit the profile of any known event. It was not the sharp, characteristic light curve of a Type Ia supernova. It lacked the hydrogen signature of a core collapse supernova from a massive star. It was not the rhythmic pulse of a variable star, nor the predictable outburst of a known cataclysmic variable. It was simply there, and then it was gone, leaving behind a single, profound question: what was it? This event is a classic astronomical mystery, a placeholder for the truly unknown. With the data in hand, scientists can only propose fascinating possibilities, each a glimpse into a different kind of cosmic catastrophe. One strong candidate is a stellar merger. Imagine two stars, perhaps white dwarfs or a pair of main sequence stars, locked in a decaying orbit. As they spiral closer over millennia, tidal forces grow immense, finally causing them to rip into each other and coalesce into a single new object. The violent collision would release a tremendous burst of light, a luminous red nova that could match the transient, slow, brightening glow. Another compelling idea is a tidal disruption event, but on an unusual scale. If a star wandered too close to an intermediate mass black hole hidden within a star cluster, the black hole's gravity could spaghettify the star, stretching it into a stream of incandescent gas. As this material swirls into a temporary accretion disk, it would produce a flare of optical light. This could explain the transient if the black hole was of just the right mass to produce a flare that was brighter and longer than expected from a stellar mass object, but fainter and quicker than one from a supermassive giant. Yet these are just the explanations we can imagine. The most thrilling possibility is that this unexplained optical transient represents something entirely new, a class of astrophysical event waiting to be defined. It could be the signature of a magnetar flare with unique properties, the birth cry of an exotic black hole binary, or even the aftermath of an asteroid-sized body colliding with a neutron star. Its value lies in its ambiguity. In a universe we are mapping with increasing precision, such pure mysteries are rare and precious. They are the blank spaces on the map, the cosmic anomalies that remind us our catalogs are incomplete. The Pinwheel Galaxy, having shown us distorted arms, silent hearts, and runaway stars, saves its most elegant lesson for last. That single, nameless flash is a promise. It tells us that for all we have discovered, the universe always holds one more secret, ready to appear in the darkness, challenge our understanding, and then vanish, leaving only the echo of a question and the irresistible urge to keep looking. 25 strange phenomena, all contained within the spiral arms of a single, stunning galaxy. From a supernova that broke the fundamental rules of stellar mass to a silent heart where a monster should roar, the Pinwheel Galaxy is far more than a pretty picture. It is a dynamic, chaotic, and deeply mysterious cosmic ecosystem. Each puzzle we have explored, whether a warped disk of hydrogen or a star that might hide another star within it, serves as a stark reminder that our understanding of the universe is perpetually under construction. M101 is not merely a subject of study, it is a full-scale laboratory. Its distorted arm is a test of gravitational theory, its anomalous cepheids a challenge to our cosmic mapmaking, and its candidate Thorne-Zitkow object a probe into the most extreme nuclear physics. Every strange flash, every silent void, and every runaway star is a piece of a grander puzzle. Solving these local mysteries provides the keys to unlocking universal secrets, from the nature of dark matter and the growth of black holes to the very life cycle of galaxies themselves. So, which of these 25 phenomena captured your imagination the most? Was it the ghostly dark matter halo holding everything together, or the violent, episodic death throes of a wolf-rayed star? The universe is filled with such wonders, each galaxy holding its own catalogue of the bizarre and unexplained. Let the enduring mysteries of the Pinwheel be an invitation to look up and stay curious, for the greatest discoveries always begin with a single, unanswered question.